Thank you, Antonio, for this kind introduction. Good morning to all. Indeed, today we are going to talk about radio astronomy. It's part of the electromagnetic spectrum, which has so far not been very much discussed during this SIDC seminar. So thanks once again, Antonio and Chris, for giving me the opportunity to talk about this. So we are looking at this part of the electromagnetic spectrum, which is bordered on one side by the ionospheric cutoff, which prevents radio astronomers to see radio waves from the sky at low frequency. And on the other side of the spectrum, we have also kind of boundary where gases in the Earth's atmosphere start to absorb some radio waves coming from the sky, in particular like water vapor or oxygen, for example, in the atmosphere. But in between, we can make pretty much good observation from the sky. Radio waves are essentially known for different applications that they have in our daily life. They are used for broadcast system. They are used for telecommunications. They are used for Wi-Fi, TV, etc. A lot of services which are very detrimental for radio astronomers and produce interference with respect to our observations. So I hope I will have a bit of time to talk about this at the end of my talk. So I was going to say that radio astronomy or radio waves are the first part of the spectrum which was explored by astronomers outside white light. But in fact, I read on Wikipedia that actually Herschel had made some infrared observation of the sun in the beginning of the 19th century, so it doesn't hold anymore, but it's still a pretty old story. Radio waves were discovered by Hertz in the late 1880s, and less than 15 years later, there was a first attempt to observe something coming from the sky. There is a French guy by the name of Charles Norman who set up an experiment in the French Alps, so near Chamonix, on the glacier of Bosson, the Glacier des Bossons. So he had put a pretty big antenna to look at the sun with an antenna which was quite interesting. He was saying that if the sun is the brightest source in white light in the sky, it should produce a lot of radio waves. And we still now know that this is true. So he put this antenna on this glacier, and basically he observed nothing. So this was a failed experiment. It's not sure why it didn't work. He had a pretty big antenna, about 200 meters big. And the issue is that we don't know exactly at which frequency he observed, so it's quite likely that he was observing close or beyond this ionospheric cutoff, but at that time it was not known. And also he made his observation in 1901, in fact in the fall of 1901, which was very close to the solar minimum of that time. So possibly he had accumulated two problems to observe solar emission. And it actually pretty much killed the field of radio astronomy, because it took another 30 years before there was another attempt to look at the radio sky. In fact, it was not an active attempt. Karl Jansky in 1933 made the first discovery of radio waves coming from the sky. He was an engineer working at Bell Laboratory, and they were investigating extra noise in their wireless system, and so he had to look for natural noise. He discovered some coming from the Earth's atmosphere, from a thunderstorm, for example, and he also observed with this antenna, which is basically a kind of gigantic dipole. He observed some signal which had a 1 year period in time, and so he could link it with a celestial source. In particular, he discovered the radio emission coming from the Milky Way. And then there is an important guy who is kind of a genius, who is Rotter Weber, and he discovered actually it's actually Weber. I made an error. He discovered the first emission coming from the sun. So he was kind of he was a self-made man. He was not an astronomer. He was a radio ham. He was working for a radio ham company in the US. It's actually also in astronomy there are always coincidences. It happens that his mother was a school teacher, and she has, as a student, she has a guy named Edwin Hubble, who had also his name in the field of astronomy. And basically, this guy was very much interested by the results of Karl Jansky, these results were published in the New York Times at the time. So he wanted to replicate his measurement. And basically, he built in his own garden the first ever radio telescope that was used to observe the sky. And basically, he is equivalent for radio astronomy of Galileo Galilei, because he's the first to have pointed a telescope in the sky. So he should have his name close to Herschel, Galileo, and other important figures. So these are the first measurements he published. Well, first, just before the war, so he repeated the experiment of Jansky, and so he published it in EPG. But he said at that time, well, I could not observe the sun. There was no signal coming from the sun. And then he repeated his measurement during the war, and by going to a lower frequency, his instrumentation was sensitive enough to be able to see the sun. And these are the curves published also in a astrophysical journal in 1944. And the sun is actually different. So it's a telescope which could not move in our angle. It could only move in elevation, so it was fixed. And so the sun would pass in front of the beam of his telescope. So you would have a bump in the record of his receiver. When you have two bumps, it means that you had the sun plus another galactic source, and these measurements are made in winter, where the sun is passing close to the Milky Way, so you could see both the sun and the Milky Way on the same day. And another interesting point here are these spikes that you see on top of this curve. These spikes are the first mention of interferences. These are due to cars passing by close to his garden. And so in this first paper, he also mentioned the fact that there are interferences produced by humans. Another important historical paper are this one published in Nature in 1946. This is the first mention of a space weather event, in fact. So it's published by Hay. So it was at that time where you could publish one column paper, because you start here and it ends here, basically. Hay was a British astronomer. He was working during the war as a radar operator protecting the coast of the UK from the bombing of the German army. And he mentioned that in 1942, his radar were jammed by solar emission coming from the sun, and that essentially there were intensities which were 10 to the 5 times stronger than what we could expect coming from the sun from a black body at 6,000 Kelvin. It's also an important point to mention that it was linked to white light flares, which was observed by optical observatories. And so another interesting point at the end of this article is the fact that they say this radio noise reported by Mr. Hay was the earliest of the terrestrial phenomena observed, preceding the fade out of the magnetic storm. Similar observation will be looked for with much interest. This is basically the start of the space weather science. Everything is in this first paper. So enough with the history, because I could make a full seminar on the history of radio astronomy. How do we observe the radio sun? Well, we make different kind of observations. The first one is to make imaging of the sun. And as you know, the accuracy of the spatial resolution of a telescope is proportional to the wavelength at which we are observing, divided by the diameter of the telescope. And since we are observing in the radio range, we have a pretty big wavelength. So the only way to make imaging is to do interferometry. So interferometry is essentially a way to calculate the Fourier transform of the source that you want to image. And you do so by calculating the coherence of the signal that you receive between pairs of antenna. So it's better if you have a lot of antenna on the ground, because you can then sample a lot of points of this Fourier transform. You can do this kind of imaging on today on a pretty wide range of frequencies, from around 60 MHz for instruments like LOFAR until a few hundred of gigahertz for instruments like ALMA. But there are a lot of issues with solar imaging. The first one is that the sun is a big source compared to other astronomical sources. And this poses some problem because usually the spacing between the antenna is not small enough, and so it's difficult to get the large-scale structure. So antennas which are very close to each other are able to sample the large-scale structure on your sources, and antennas which are very far apart can look at very small spatial details. And the sun is so big that usually you don't have enough antenna close to each other to sample a large-scale structure and to have an accurate flux of reconstruction of the sun. And this is seen, for example, in this data coming from the Nançay radio heliograph. You have to the left the sampling in the Fourier domain of a solar image. So you see that there are a lot of holes in these images. So there are empty spaces here and here. And even in the central square, you see that there are dots and holes between these dots, and this is due to the fact that the sun, that the spacing of the antenna on the ground is not small enough. And this makes this kind of image where you have a lot of artifacts. So you have aliasing in particular. So this, you see this brightness here and here, here and here are repeating images of the sun. And the contrast of the image is a way to overcome this problem is to use the Earth's rotation. So the geometry of the array as the sun moves in the sky will change with time. And if you integrate it in time, you will cover the holes that are in this snapshot images. And indeed, the resulting image is much clearer. With the artifact, there are no aliasing anymore. But here we have about an 8-hour integration. You have to assume that your sun will not make any flares during these 8 hours. And of course, that there is, in 8 hours, the sun rotates, so small structure will be smeared out by this kind of procedure. Also, a problem which is important at low frequency is that we have the ionosphere, which is producing some artifact, and in particular, it's, you know, that in white light astronomy we have the Earth's atmosphere, which is producing this shrinking of stars, and in radio astronomy it's even worse. Image of the sun. So here it's in white, it's the optical sun. We have a source which is linked to an active region, and if the ionospheric conditions are bad, you can see that during the day the source will move pretty much by several solar radius just because of ionospheric effect. So it's a challenge to make good images of the sun, especially at low frequencies. But we can do them anyway. So this is an overview of a quick overview of several solar instruments. You have here, so the Nançay interferometer, it's 1.6 kilometer long. There are also antennas there, 1.1 kilometer there. And here it's a collection of quite sun images of the sun at from 445 megahertz down to 151 megahertz. So at high frequency, you can guess that this image looks like more or less what you see in UV telescope. So, and at low frequency, you have a very different sun. The reason for this is that we are not looking at the same layer of the solar atmosphere. The lower you go in frequency, the higher you go in altitude over the solar surface. And in particular, in this low frequency, you start to see structures that you can assimilate to streamers or a large-scale structure linked to filament, for example. While at higher frequencies, you see, for example, individual active region, filament channel, and small coronal holes. Other instruments that scientists are using to study the sun, for example, the VLA, well-known instrument in the United States. So it's not a solar dedicated instrument, so it means that you can observe the sun by doing some campaigns. But it requires that the VLA is what is called a compact mode to be able to sample this small baseline. So you need to move physically this gigantic antenna with special trucks on a compact formation. So it's not something that the VLA people are doing every day, because it's a lot of trouble and recalibration after the antenna has moved. But there are several solar observations. Here is a nice one from Stephen White at 4.6 gigahertz, and you see that indeed we are at very high frequency, and we see a sun that you could recognize if you are an optical solar astronomer. If you go higher in frequency, we have instruments like the Nobeyama radio heliograph. So here you see that the antenna are very close to each other, so we are able to sample accurately the large-scale structure on the sun. And this instrument is doing daily observation of the sun at two frequencies, at very high frequency. And here we are looking at layers which are in the chromosphere of the sun. You see filament, you see nice flaring event here. The last instrument I want to mention is a low-power telescope, which is on the other side of the radio spectrum. It's an instrument. It's also an interferometer with several stations located in the Netherlands and also elsewhere in Europe. And it's a special instrument in the sense that it can make both dynamic spectra of the sun and imaging. So it's a new trend in radio astronomy. The VLA has been updated recently to do the same, but in a very narrow range of frequency. But indeed, it's always important when you are doing solar radio astronomy to also not only having images, but to be able to characterize what kind of burst that you are seeing in these images. And the only way to do it is to look at this dynamic spectra. So dynamic spectra, it's useful because apart from the quite sudden emission, which varies relatively slowly from day to day, indeed, solar radio emission linked to solar eruptive events can vary on time scale of a few milliseconds up to a few hours, and their intensity can vary by several orders of magnitude. And dynamic spectra are the only way to probe and to characterize each of these emissions. So here it's a cartoon, classical cartoon of eruptive event occurring on the sun. Sorry, it's in French, but I guess you will recognize what's happening there. So you have a reconnection event there. You have a magnetic structure which will become a semi. You have the post-flare loop arcade linked to the flares, and basically around the reconnection site, electrons because in the radio what is important is electrons. The ones that are accelerating downward are producing high energy signatures in X-ray, soft X-ray, hard X-ray, and also in high frequency radio emission. We have, for example, sensometric emission. Electrons, which are essentially accelerated upwards, are producing other kind of radio emission at lower frequencies that you might have heard of. So we have, for example, type 3 bursts, which are going along open field lines. These are electron beams accelerated along open field line going outward. We have, for example, type 4 bursts, which are electrons trapped in the magnetic structures of the CME. You have type 2 bursts, which are produced by shock waves. So in this cartoon, it's depicted at the front of the structure, but we now know that it's not always the case. And each of these types can be distinguished by spectrometers and spectrograms. So quickly, example of spectrograms taken from our instrument here in Humain. We have example here of type 3 burst, so fast drifting radio structure linked to electron beams accelerated during phase. They are typically electrons going at the speed of light. We have complex events with type 3 burst. These oscillating and pulsation structures are often part of what is called type 4 burst. And we have a weak type 2 burst here, so a slower drifting structure, but it's better seen in this next event. A slow drifting structures associated with radio, with a shock wave, and also a high frequency counterpart, so electrons accelerated close to this reconnection region. And finally, the quiet sun emission. So the sun outside eruptive event varies on a solar time scale from day to day, depending on how many active regions there is on the sun. So solar emission, contrary to our colleagues who are observing galactic radio emission, for example, are not emission lines. So in the galaxy, if you point a telescope towards the galaxy, you can look at the hydrogen line from molecular hydrogen in the galaxy. But the sun emits at a continuum. It's essentially thermal emission because the solar atmosphere is hot, so it emits in a wide spectrum range. And we have also gyro emission, so electrons emitting at the multiple of the local magnetic field, electrons which are trapped in magnetic structures of active regions. And it's funny to look at the first observation which were made in that field. So the F10.7 index was started in Canada. It was frequency was chosen because the first radio telescope there were military radars working at 10.7 centimeters of wavelength. And so Covington was the first to have made this observation. He had set up an experiment for solar eclipse. So he wanted to look at this solar eclipse with his brand new telescope. And they had made a careful calibration of those. And when they applied the calibration results for other days than the eclipse, it didn't match very well. And he is known for having said that, yeah, it was a problem, that it was seen as a problem at that time, that the solar emission was varying from day to day. But now we know it's a very important index of the long-term activity of the sun. And indeed, we are now observing beyond the sunspot index, radio measurement of the daily solar flux is the longest measurement of the long-term trend of the solar activity. So now we are doing this at several places around the world. So the primary source of the F10 point index is in Canada, at Penticton on the west coast. There is also another important observatory in Japan, the Nobeyama Observatory. They have been observing 4 frequencies for almost the same amount of time as Canadian. And then there is a network of instruments from the US Air Force at different places around the world to have daily monitoring of the sun. And I hope soon we are working hard to add an extra point here in Belgium to have an extra measurement point. And basically, this is the measurement from not the whole observation, but for the last 40 years, which is at different frequencies, which is very reminiscent of indeed the solar cycle as it can be seen from the sunspot index. So how can we make this kind of measurement? Well, we need an antenna and we need a telescope. So an antenna is characterized by its gain. So usually we are using as a reference a perfect antenna which doesn't exist. So it's an antenna which would radiate or receive equally in a solid angle of 4 pi. But a real antenna has a preferential emission direction, and it gives a certain gain in that direction. Usually, this gain is determined by the shape of the antenna, by its electrical properties, also by the local environment in which this antenna is placed, and we can calculate this kind of gain, and this is a calculation made by Antonio for one of our projects, the Space Interferometer. So again, it's usually characterized by its main beam. This is usually the maximum of the gain that we use in data sheet, for example. And you see these side lobes around the main gain, which in radio astronomy we try to put as low as possible to prevent receive signal from other sources than the main direction at which we are looking at. There is an important parameter in radio astronomy that we are using is the effective area, which is linked to the gain by this formula. I will come back later to this. So different kind of antenna. The simplest one we can think of is a dipole antenna. It's essentially a rod or two rods which are measuring the electric field of the incoming electromagnetic wave. So the electromagnetic wave will drive electrons in the rod, oscillating in phase with the incoming electric field, and you will essentially measure the voltage resulting at the output of your antenna. And if the size of your dipole is half the size of the wavelength, you have an optimum resonance between your dipole and the frequency at which you are looking at. And this is called then a half-wave dipole. This kind of antenna are pretty much isotropic, so they see pretty much the whole sky, except in the direction of in this direction where they don't see at all. But on both sides they are pretty much isotropic. And from this simple design, which is still very much in use, we can derive several kind of antenna which are used here on the plateau. So the first kind is Yagi antenna. This is used for example, from our colleagues from the brand network. So you have a dipole at the center here, which is connected to your cable, and you have two what we call parasitic elements, which are not connected electrically to this cable, but there is one which is behind the dipole, which is slightly longer, which will act as a reflector, and there is one in the front of the dipole, and it will act as a director. The game is to go from this isotropic gain to a one which has a preferential direction. So essentially, these two components will produce some destructive interference behind the dipole and constructive interference in front. And the resulting gain, it's shown here by a calculation by Antonio, is that the fact you have a gain which is shifted into one direction and diminished into the other one. The kind of antenna which we are using here is the log periodic antenna. It's also a collection of different dipoles of different lengths. Contrary to Yagi antenna, each of these dipoles is connected to what we call the field line, so to the cable to which we will receive the signal. And it's made in such a way that each triplet of rods will act a bit as a Yagi. So we have a forward gain in one direction, and we will reduce the gain in the backward direction. And the fact that we have several rods of different lengths means that this antenna is inherently broadband. So we can observe a wide range of frequencies. The lower frequencies are observed with the longer rods, and the higher frequencies with the shorter ones. This is an example again of a calculation made by Antonio of this antenna which we are using in Humain. So you see that the gain at different frequencies is shifted in one direction, and it's pretty much identical from one frequency to the next. So we have an antenna which behaves relatively equally at all frequencies. And indeed, we should look at this diagram this way. So the forward gain in this direction. The last derivative of dipoles, I told you, is what we call fat dipoles. So I told you that the dipole was essentially tuned to one frequency, but of course, as radio astronomers, we want to observe a wide range of frequencies. And the black magic of antenna design tell you that if you change the shape of a dipole and if you make it fatter at some extremities, you can extend the range of your antenna, but it has a cost in the sense that your antenna is not very well matched electrically. So you have to compensate it by active elements. So you have basically to put an element which will extend and make the response of your antenna flatter than it can be without active elements. So in this white box, we have a small amplifiers and a balloon, which will make the resulting gain. So we have a peak around 50 mega, which corresponds to the physical size of the dipole, but the fall-off is less than it would be if we would not have any active element. Now, so it's a family of resonant antenna. Another kind of antenna that we are using in radio astronomy is horn antenna. So it's basically the electromagnetic equivalent of this device used by this famous Belgian scientist. It's essentially a way to make a soft transition between electrical properties of free space and the one that occurs in your waveguide. So basically, you make a soft transition between the impedance of free space and your impedance of your lines. It can be seen also as the equivalent of a trumpet. We like horn antenna because they are relatively easy to model. You can almost completely calculate their properties in an analytical way. They result also in a high gain antenna with low side lobe compared to this resonance. And they are often used as a feed antenna. So like in this case, so we have a parabola, and we have at the focus of the parabola, we have a horn antenna. It's a sketch of made by Antonio for a new system that we are working on. And these horn are also used as absolute calibration devices. Good example are this instrument. So this is a diagnostic instrument which was used in the 60s in the US in the Green Bank of the Observatory in West Virginia. It was called Little Big Horn, and it was meant to observe only one source outside the sun. So we have the source which is called Cassiope, which is a remnant, if I'm not mistaken, of supernova, and it's very strong. And since this kind of instrument can have a very narrow beam and high gain, it was used to measure precisely the variation, the flux of this radio source. So it could make one measurement per day for several weeks during the year, but it could help to calibrate the other telescope of this radio observatory. This horn antenna is also very famous because it's the one which has been used by Penzias and Wilson to measure the cosmological background at 2.7 Kelvin. And it's also a horn here with a reflector. The horn is here, but there is also a reflecting system here to be able to point at different directions in the sky. In solar physics also, we are using a horn antenna to cross-calibrate other telescopes. So here's a system which is used by our Canadian colleagues to calibrate the F10.7 index. So they have a classical radio telescope to track the sun during the day, but they also make one-day measurement of the solar flux with this transit instrument. So it's a collection of two horns which can move in elevation, but they cannot move in our angle. So it's a transit instrument, and they can see the transit of the sun in front of their instrument, and it's an intercalibration also way to calibrate their daily measurement of the F10.7 index. So usually speaking, when we have a resonant antenna or a horn, we want to put it on a dish parabola to have what we call a telescope. An equivalent of an optical telescope with a primary mirror and a focal plane where you have your feed antenna. So typically, so as I say, the angular resolution is proportional to the wavelength divided by the diameter of your telescope. So in this collection of solar radio telescopes, you can guess that this one are observing the low frequency and this one are observing the high frequency. So basically, they all have approximately the same field of view, but they are working at different frequencies. You can also say that at lower frequency, you don't need plane mirrors. Basically, if you have inhomogeneities or holes in your mirror which are smaller than a tenth of the wavelength, your mesh will act as a real mirror, so you can use it as a parabola. And in Humain, right now, we have a mesh parabola that we use to observe the sun. If you are using a plane mirror, you can build a big telescope, but then you have a compromise. If you build a big reflecting telescope and you point it at the sun, you start to have thermal problems with your telescope. For example, the ALMA antenna, which are approximately 15 to 20 meters wide. When they are pointing at the sun, the focal plane can get up to 100 degrees. So it starts to be an engineering problem to evacuate all this heat from your setup. So typically, the solar telescopes are small. This is also a picture from the Nobeyama polarimeters with very small telescope for the 80 gigahertz observation and bigger one for the low frequencies. So typically, so we have a parabola, and then we have here a feed antenna, which is here a horn. But it doesn't mean that if you have an antenna of that diameter, that you will use all this parabola. It depends on the field of view of your feed antenna that you put as a focus. So sometimes you can under-illuminate your parabola, and this is often something that you want because it prevents, it diminishes the the fact that you can see others. I mean, it makes your system more resilient to outside emission. This kind of system are relatively easy to. So what I want to say is that the resulting gain of your parabola depends essentially of the aperture of your system, but this is, you have a factor which is not equal to 1, and which takes into account how much you illuminate your parabola with your field antenna. It also takes into account the quality of your surface. It takes into account the impact of the supporting struts that are holding the field antenna on your parabola. So this factor is never equal to 1. In practice, it is always equal to 0.6 in average. If you make the analytical calculation of this kind of system, this is what we did for our new parabola in Humain, you can, for example, have this result. So you have your main beam. You can calculate so the beam of your telescope. You can calculate the gain, and if you apply this simple formula and this simple formula, you see that there are matching pretty well analytical calculations that we can make. So these all of them are pretty good in evaluating the performance of parabolic systems. So what do we measure when we have a telescope like this? At the output of your telescope, what you measure is power, so in watts, or power in a certain frequency range. So it's a power divided by your bandwidth, so power per hertz. In radio astronomy, we are using a concept which is called temperature, which is very useful because we can refer it also to brightness temperature of sources in the sky. When you make a measurement, you measure something coming from your telescope and a noise which comes from your receiving system. So we make this distinction between what we call the antenna temperature and the temperature of your system. And the antenna temperature is itself made of several components. What you want to measure is the source, but you not only see the source, but you see the sky around the source. You see some power coming from the atmosphere. You see some power coming from the ground through your side lobe. You can see also power coming from, if you have a mesh parabola, you have part of your system which goes through which sees through a parabola. You can have some diffraction on metallic support of your field antenna. Here it's mentioned, yeah, you can have the galactic background. In fact, this is how Gas and Wilson discovered it. They wanted, in fact, to observe the Milky Way. So they made a precise calibration of their instrument, precise assessment of the noise of their system and of their antenna, and they find a horripilating 2.7 K difference between their simulation and their measurement, and this made history and gave them the Nobel Prize. So once you have evaluated each of these parameters, in fact, what you are interested in is not the antenna temperature, but it's the flux of the source. So you measure a power or a power per hertz, and you are interested in the intrinsic emission from the source, which is this parameter, this S nu, which is in watts per meter square and per hertz. The two relate in that way. This is what you measure. This is what you want to estimate. And you can multiply by the effective area of your telescope, which I was mentioning before, which is linked to the gain of your overall telescope. Now, if you do a little bit of math, you can see that your flux density is essentially related to the solid angle of your telescope and is proportional to this solid angle, which means that if you have a telescope which is the size, which solid angle is the size of the sun, the temperature that you will measure will be the brightness temperature of the sun. But if you have, like in this case, a beam which is wider, you will measure a brightness temperature which is smaller than the intrinsic brightness temperature of the sun. And so you can estimate the brightness temperature of a source if you know its size and if you know the gain of your telescope. So typically, for example, in Humain, we have at this frequency with our telescope, we have a gain of about 30 dB, and yeah, we know that what we measure in terms of brightness temperature when we point it at the sun is approximately 200 times smaller than the real brightness temperature of the sun. Typically, the flux density related to the sun is about 10 to the minus 22 watts per meter square per Earth. So it's rather small compared to our daily life, but it's 10,000 times typically than other radio astronomy sources. In radio astronomy, we use the Jansky, which is unit, which is 10 to the minus 26 watts per meter square per Earth. It tells you that the sun is a very strong radio source. And indeed, if you look at this diagram, I don't know if it's very sharp, but so you have different noise contribution to a typical radio telescope. The strongest one is the sun. Here you have the antenna, the resulting antenna temperature. In that case, if you have a telescope which has a beam width which is the size of the sun, so the sun is dominating in a wide range of frequencies. You have the cosmological background here. You have a galactic background here, and you have also man-made sources, so interference basically, which could be extended also in other range of frequencies. How do we estimate the system noise? Well, if you have your receiving antenna, you usually plug it with a cable to some electronics, which will filter, amplify, or make other things to your signal. This electronics will be connected also by another cable to your receiver. All these cable, electronic, and receiver, they introduce some noise. For example, a cable will not propagate your signal without attenuation, so it will attenuate your signal depending on the length and the frequency, depending on the length of the cable and on the frequency at which you are observing. For example, an amplifier will amplify your signal, so it will give some gain, but it will do so also by introducing some noise in the original signal. So we have ways to calculate the overall noise of the system, and it's given by what we call the Flux formula. Flux was actually the boss of Karl Jansky at the Bell laboratory. It's a relatively easy formula, but it basically tells you that the first element in your chain is the one which is influencing the noise in your system. For example, in that case, we have a cable. The noise of the cable can be calculated by the physical temperature of the cable, basically, and multiplied by the attenuation of the cable. So if you have a strong attenuation, you will have a certain temperature, a certain noise in your system, but it will be also present in the next successive stage of your system. So if you have a strong attenuation, it will be seen by the other component of your system. If you have an amplifier with a very important gain, so if G is very important, everything which is behind the amplifier will have a relatively low noise. So in a perfect system, you would like to put a very good amplifier at the beginning of the chain because it will diminish the noise in your whole system. Here in Humain, it was not possible to do so because we had no space physically close to the antenna, so we had first the cable and then the amplifying system. Its result, for example, in Humain, to typical noise of this magnitude. So this is physical room temperature noise, and these are the resulting noise of the system at different frequencies of our receivers. So if we have estimated the noise, parasitic noise coming from the antenna, the system noise, we can try to make calibrated measurement of our signal. This is an example of a quiet sun observation made in Humain on November 4th, 2015. It's a quiet sun until that time of the day where we have a strong radio burst. But here, for example, we are interested in measuring the quiet sun level at 611, so the blue curve. So how do we do it? We make a measurement at the end of the observation when the telescope is put back at meridian, so far from the sun. So it's considered to be a measurement of the sky. And we make a measurement before noon. So at noon on that day there was a flare, but so we make it just before noon. It gives us a measurement of the sun plus the sky. We have estimated also the noise of the system, which we assume is relatively constant during the day. So the difference between this measurement and this in dB can be related to the difference in power. And so if you do the number, you can estimate that the antenna temperature, if you point at the sun, is approximately 3000 Kelvin. And as I said earlier, since we have a quite large beam, we know that it's not the physical temperature of the sun. We have to compensate by this factor, and then we find something which is approximately 7.5 10 to the 5 Kelvin, and there it's something which is quite close to coronal temperature, or at least a transition region temperature, which we believe it is when we are observing at approximately 600 megahertz. We are in altitude range which corresponds to the lower solar corona, where we can see this kind of temperatures. So basically all the receivers are working with this principle. A class of receivers that I want to mention are spectrometers. I don't know how much time do I have? Not much time. So basically, spectrometers look at a wide range of frequencies, and there are different families of receivers. Either in the old time we were observing with multiple receivers in parallel, so it was called multi-channel spectrograph. So basically, you would have one input, and then you would have different stages which would divide the signal into smaller narrow bandwidths, and you would end up with like essentially 120 different small receivers, each producing an output at a very narrow frequency range. They were very good frequencies, but obviously you cannot multiply the number of channels at infinite, so because the complexity of the system becomes too much. Another family of receivers is what we call the sweep frequency receivers. This is the case of our Callisto instrument. Basically, you have a very narrow frequency window that you will shift in frequency in a certain frequency. So you have a very narrow window that you shift in frequency in a certain frequency range. And with the Callisto, we do it with a step of 62.5 kilohertz. It's a good way to go fast, but usually as you are going fast, you have a system which is worse in terms of noise compared to multi-channel receivers. Another family is this one. I don't know if I want to give much detail, but basically you want, like multi-channel receivers, you want to split your band. If you have a very large bandwidth like it is, you want to split your band in smaller one that you can input into a system that will digitize your signal, and then you can make a FFT with a computer or a dedicated board. But I think I will go fast. And what we are using now in Humain is a kind of mixed system. So it's a system where we have a wide window. So instead of having a window of 300 kilohertz, we have a window of 25 megahertz. And we split it in frequency. But in this window, we make, for each of these 25 megahertz step, we make a FFT of the incoming spectrum to produce overall dynamic spectrum. And we are doing it with off-shelf receivers and using open source software. So I'll go fast now because I guess most of you know what is Humain. Maybe for our guest investigators it will be new, but so we are here in Brussels. We have a radio astronomy station in the Belgian Ardennes in Humain. It's a site of several instruments. Some from the there is no okay. So there is different instruments, including our solar telescope here. This is a close-up view of our system. We have a 6-meter dish. No, it doesn't work. So we have a 6-meter dish with 2 antennas, one on the side for the low frequency, one at the focus for the higher frequency range, and we have essentially 3 receivers which are covering a frequency range that goes from 45 till approximately 1500 megahertz. This is an overview of our system. Callisto, so is the SWIP receivers. It's a part of the network. It goes. It's working very well, but it's probably a bit old as a technology, but it's still very good. And the 2 new digital receivers are ARCAS and HSRS, which have been put in place starting in 2015, if I remember right. So now a preview of what we are working on. So we want, as I said earlier, to measure the flux of the sun at different frequencies for space weather application and for networks and other applications. So we want to observe this list of frequencies. Some are linked to are important for our GPS colleagues. Some are important for monitoring what's happening in air traffic radar. We have bands which have been deemed important by people like Thierry Dudok for orbitography. There is important band, the F10.7, and there are other bands which are useful for radio astronomy purposes that we want to observe. This is a preview of the system that is being developed in our lab. It's a bit messy, but it's being calibrated right now. We have this is a signal coming from the antenna. It goes through, we filter the signal to isolate a certain band. We have amplifiers to amplify a signal, and then we have the receivers. We have a noise source to calibrate our signal, which will be put in the box. Some other component to, for example, the attenuator allows us to have different level of calibrating signal, etc. So this is a preview of what we are doing. Preview of the receiver. It's a small digital receiver, very the size of half the size of my laptop, to say the least. This is a preview of the software that is controlling the receiver. So this is the receiver is there. So everything can be done digitally. So we can change the frequency by software. We can multiply the signal. Here we want to measure intensity and the circular polarization. So we have 2 perpendicular. So we have one antenna which gives 2 orthogonal signals. So we can calculate stock I and stock V parameters because we have 2 orthogonal electric fields. And so we make all the calculations, the sum and the subtraction to calculate the stock I and stock V, and we try to store it in a file. So this is this kind of programming that we are doing for this instrument, and this is a preview of the mirror which was installed in December by Antonio and Mark and the technical service. So this telescope is an old telescope from the interferometer. It has not moved for 50 years. It has been repaired mechanically. but we have recently finished to install the plane parabola and also the support of what will be the focal plane of the system. And so together with IDIN, we are working hard to make it ready for the visit in May. But I'm sure it will be ready by that time. Another preview of what we are doing is a spade telescope. So the fat dipole I was mentioning is used as an array of dipole in Humain. We are doing basically interferometry also there, not to imaging because the instrument is not big enough. It's a square of 20 meters by 20 meters, but to add coherently the signal coming from each antenna to have better spectra. So it's a kind of mini LOFAR, but without the imaging capability. And we are also working hard to make it ready for the May visit, but okay, there are only 24 hours per day. Quickly, the last part is the problem of interference and spectrum management in radio astronomy. Like I said, the radio astronomy is a passive service. It means that it doesn't emit, but it only receives from the sky. And it also receives from unwanted sources like man-made interferences. So there are international rules to protect radio astronomy. A famous one is that one. It gives a threshold of interferences that are allowed in radio observatories. And astronomers make sure that these are respected. That's why we are fighting when there are some wind turbine projects who wants to be established close to Humain, because we want to keep the signal below this reference level, which are published in this recommendation. Typically, I don't know if you are aware of that, but the radio spectrum is very well regulated. This is a view of the occupancy of the radio spectrum by different services. In the United States, it's the same in Europe, but I took the case of the US because they had a nice graphical output. So each block here is a service making use of the radio spectrum. So the game is that none of these services interfere with each other, and radio astronomy has only these boxes in these red boxes in the spectrum. So we are indeed a small user of the spectrum, even if our target is emitting over a wide range of frequency. So it's a challenge to make radio astronomy these days. This is seen in this wide worldwide plot of interference level referred by Callisto. So when it's a green, it's more or less okay. When it starts to be purple, yeah, it's a high. It's an area which is not very good for doing radio astronomy. And in Europe, I mean, I think they lack enough color to indicate the level of interference, so they repeat the color. So in Europe and also in the US, in Asia, it's essentially they are essentially very bad place to make radio observation because there are a lot of interferences. That's why new instruments like SCA are put in isolated place, like in Australia and also in South Africa. There is ALMA also in Chile, which is a very good site, far away from any interferences. And example of interferences, this is specifically good spectrum from Artemis instrument in Greece. These are called zebra bursts, so they are indeed solar radio bursts, which are seen in some intense radio emissions. And these are other kind of zebra bursts. These are interferences produced by LED lamps. And here, a grass, someone cutting the grass around the telescope. They look very much like zebra bursts coming from the sun. So if you are not, if you don't pay attention, you can publish papers which are essentially rubbish. That's why it's very good to know the electromagnetic environment of your telescope. And I think this is